Okay, let's start today's session. Good afternoon, everyone. Thank you for joining for this eighth interaction session. So, this session, interactive session, is for the NPTEL course Experimental Physics 1. The course instructor is Professor Amal Kumar Das from IIT Kharagpur, and I am Mrinalini, PMRF Research Scholar from School of Physics, University of Hyderabad. As you know, this session happens every Saturday from 3 p.m. to 5 p.m. and all these sessions are recorded and uploaded on the YouTube channel. That link also is provided in the drive along with these PPT materials. So let's proceed for today's session. So let's have a recap of last week's what we discussed. Last week we discussed this experiment where we wanted to determine coefficient of viscosity of a liquid. We understood its theory, and using Poiseuille's law we worked out the working. This is actually the working formula for this particular experiment that we had derived based on Poiseuille's law. The next was we understood how when a spherical body is thrown in a is left to drown in a liquid column as shown in the diagram here, what are the forces acting on it and what is the maximum velocity it attains, which is called the terminal velocity. And here also we had worked out the working formula which is given here, and based on this we had done several problems as well as last year assignment questions. The next experiment that we had discussed was oscillations, where we understood what are oscillations, what is simple harmonic motion, what is the general equation for it, and what are the different type of oscillations like simple oscillation, forced oscillation, damped oscillation. And as you remember, the professor had demonstrated all these three different types of oscillations using this particular type of pendulum or wheel called Paul's wheel or rotating or torsional pendulum. So we had also understood how this works based on the eddy current, and we how we can calculate damping constant, time period and other things by performing this particular experiment. So this was all what we discussed last week. Now this week's experiment is about coupled pendulum. So let's understand what is a coupled pendulum. So simple pendulum, we remember a simple pendulum is a mass attached to some fixed position, and the mass is subtended or it's hanged by a string that we call it as massless. I mean it's the mass is such small that we can neglect it, and that's why we call this string massless string. So that what we consider here is that all the mass in this pendulum is concentrated in this bob of the pendulum, and this is the setup of simple pendulum. But here, as you can see in this diagram, here separately if you'll see, this is one simple pendulum. If you remove for a minute, if you don't think about this spring here, then this is one simple pendulum, this is another simple pendulum. If you do any disturbance in this simple pendulum 1 and something we do to the simple pendulum 2, they will be independent of each other. But if due to some way we want them to interact, then we need to join them. If the joining is in this form, that here we have put a spring between these two pendulums, then now they are coupled, and thus the name coupled pendulum. Here these two pendulums are not anymore independent, but they are dependent on each other, and this whole setup is called coupled pendulum. We'll understand what are the different situations that can arise when we have two coupled pendulum system consisting of two pendulums as shown here. So the equation we know for simple pendulum, we if we are displacing this by some theta or phi angle, then if we are displacing it by some theta angle, say, there is restoring force acting on it, right, in this direction opposite to the direction of displacement. We are displacing it in towards right, say, then restoring force is acting in the opposite direction, that is towards left. And when we balance these all the different forces acting, because there is force due to its mass, whereas there is force due to the tension of the string, when all these are balanced, we get a time period equation for this. Anyway, so main thing what I want to say is, so the equation is written like, consider this is the displacement y, then it's given by some amplitude and sine kx minus omega t. This is a general form of equation. Now here, if I am writing equations for this coupled system, then it will be something like this. So equation, so this was the solution for simple pendulum case. Whereas what will be the solutions and the different cases arising when such a coupled system we have. So what will be the equation of motion first for this pendulum 1? So it will be this mx dot, x double dot is acceleration actually. If in case somebody doesn't know, x is displacement, right, and velocity is dx by dt. Another way, simpler way to represent is x dot. This means derivative of x. Now acceleration is derivative of velocity with respect to time. That means double derivative of displacement with respect to time. This thing itself is what we show as x double dot. Either you can write as acceleration or x double dot. It's the same thing. So this is the force for this pendulum. The equation of motion will be minus mg x by L. Derivation actually we will not focus here much, because the professor has explained very nicely all this in detail in the video. Here we will just focus on the results, the three conditions that we are talking about, and then we'll see the experimental procedure and assignments. So our main focus is on those things. So I'm just writing here the equations. This x is the displacement made by the first pendulum and y is the displacement given to the second pendulum. The equation of motion for the second pendulum here will be, so we know otherwise if only this simple pendulum is there, then it will be x double dot minus g spell. Here, because of the spring, there is some more force acting here, so that's why this term is coming. Now this is due to tension force acting on here. It's k y minus x. This will be the equation of motion for the second pendulum. Now after solving and taking various assumptions and substitutions, as again you can watch in the from the video, you must have already seen the derivations. What we find out from this is, when we try to solve these equations, the solution of these equations, we get something like this. To solve actually this equation, we cannot solve it easily because here there is x and y, two unknown variables in both the equation. Thus, as it was shown that if we take x plus y as capital X and x minus y as capital Y, and substituting these things, we'll get a decoupled, we call it decoupled equation, because it will be, when we'll substitute these uh, assumptions or these these things in these equation of motion, we'll obtain decoupled equations. So, okay, let me write the decoupled equation also. So the equation of motions will change to something like this. After we'll do the mathematics there, it will change to this. So this is the equation which has only x variable. The another equation will change to something like this. This is y double dot plus omega naught square plus 2k by m y is equal to 0. So now there is no two unknown variables here or either in this equation, so they can be easily solved, and also they are now decoupled. Solving these equations, anyway you can see that this is simple harmonic equation, this is also a simple harmonic equation with different value of angular frequency. For this, the angular frequency is omega naught. For this one, there is some other angular frequency which is equal to omega naught square plus 2k by m and whole root of this is the angular frequency for this second pendulum in this case. Now what will be the different conditions that can happen when the two pendulums are coupled like this. So say, like as I said initially, again let me write 1 and 2. Here we gave the displacement x and here we gave the displacement y. Okay. Now say if these two displacements are equal and in the same direction, like initially they will be like this, they are coupled. Initially they will be like this, and then I'm moving this and this in same direction, okay, also by same amount. That means the displacement for both is in the same direction and by same value. What will happen in such situation? So this will be our case 1. That is x is equal to y. Means from here you can say when x is equal to y means y is this capital Y will be 0 and capital Y will be 0. That means this equation will be 0, right? When y will be 0, this equation will be 0, only this equation will be left. What does that mean? That in this particular situation, what happens is, only at particular time only one simple pendulum will be executing simple harmonic motion, and this is called in phase mode. This is called in phase mode. Oh, so no, sorry. So what does this mean is, when we give displacement in same direction by same amount and y is capital Y is 0, this is called in phase mode. What happens is, since we have given the displacement by same amount, the spring is in equilibrium. It's neither getting compressed nor getting extended. So it's in an equilibrium, and thus the oscillation of these pendulum will continue, but the spring will continue to be in equilibrium. Thus there will be no transfer of energy from one pendulum to another pendulum. This situation is called in phase mode. So whole system will be like this, is single pendulum, and there will be no transfer of energy from one to another, because this force due to this, as you see, there is no spring contribution from this spring, right? So it will be just oscillating without any getting any force acting from the spring. So this is one in phase mode case. Another case is, it's the situation if x is equal to minus y. That is, again we are giving displacement by same amount but in opposite direction. So this was case 1. Now case 2, for what we are saying is, this is one pendulum, this is another pendulum. They are coupled and I'm giving them this one x and this one y. I mean same this also I'm giving same amount of displacement, but now in the opposite direction. Either I can do like this or I can do like this. I mean same amount but opposite direction. When I give them displacement in this particular manner, so as you can imagine, if I'm giving them displacement away from each other, then this spring will get uh, extended, right? On the other hand, if I'm pushing them towards each other, in that case the spring will be compressed. So the spring uh, is not anymore in its equilibrium position. When this kind of displacement is given, this leads to, so x is equal to minus y, this means the capital X will be 0. And when capital X will be 0, so this equation will be 0 and we will be left with this second equation, where you can see there the angular frequency will have contribution from the spring constant as well, and the frequency is given by this. It's not simply the omega naught here, but plus 2k by m factor is also coming because they are coupled now, and this is called out of phase mode. These two modes of oscillations are called normal modes. These two types of modes are called normal modes. Now there is one more interesting thing that can happen. This is actually called something we already know. We are already aware of this term called resonance condition. We have read this in case of forced damped pendulum when we were doing experiment based on Pohl's pendulum. Anyway, so for these coupled pendulum system, when this resonance condition happens, and when this happens, what exactly we get to observe? Okay, so when this happens is, uh, after solving these two equations, this which was in terms of capital X and capital Y, when we solve this, we get general equation. Again, I just want to tell you the final thing instead of giving in detail. So I'm telling you the final what we'll get instead of going into much detail. The x and y that we get out of after solving these things. Okay, let me know. So the general solution after solving those things will be x, which is actually x plus y. The solution here will be x naught, the amplitude, and cos omega naught t plus phi 1, some phase, capital Y is equal to, which is x minus y, we had taken it as, so it will be y naught cos omega 1 t plus phi 2. Okay, now here these x naught y naught are amplitudes, phi 1 phi 2 are phases, omega naught and omega 1 we had already shown what are these things, omega naught and omega, this is actually omega 1 you can say, or omega, whatever you want. So this is what is here. So if we assume, again let's say, let these amplitudes say some value, and these phases are 0. Okay, then uh, if we'll solve this, from this the small x value is actually half x plus y, and when we'll do some trigonometry, actually we'll get to see the solution in this form: 2a cos omega 1 minus omega naught divided by 2 times t cos omega 1 plus omega naught divided by 2 times t. This solution for y will be half, this is small y, x minus y, which will be, okay, let me get the final form will be 2a sine omega 1 minus omega naught t by 2 sine omega 1 plus omega naught by 2 times t. Okay, so what we see from this is we'll get here, I mean if you compare it with the for the equation we get for simple, the equation we equation that is there for simple pendulum, which is a sine kx minus omega t, right? So I mean this is some amplitude, and then yeah, so amplitude is constant here, and then sine is in form of this. If we compare like this, that means, or if we ignore the phase, it's also written as a sine omega t plus or minus phi, right? We also write it like this. So here if we ignore the phase thing, then a sine omega t, if we compare, that means the sine omega t, this part is there, that means this is the frequency. What we see from here, this whole thing actually is, you can consider this is the amplitude in this situation here. This is the amplitude. So what we see when we get this resonance condition, when this happens, we'll see, but when this resonance condition happens, the amplitude is also oscillating. The amplitude also starts oscillating, and when this condition happens, we get two types of frequencies. Okay, I need some. We get from here these this omega 1 minus omega naught by 2 that we saw here, which is making the amplitude to oscillate. This is called coupled pendulum. This is the frequency of coupled pendulum. This is the frequency of the coupled pendulum. So the coupled pendulum oscillates with this frequency, which is omega 1 plus omega naught by 2, and this omega beat. So in this situation there is this another frequency that we are getting, which is the beat frequency of variation of the amplitude. Wait, frequency of variation of amplitude. Okay, sorry. Omega 1 plus omega naught by 2 is the frequency of the, as you can see from here, as this here omega is the frequency of oscillation of simple pendulum, that one pendulum, right? The same way here, if we compare, this omega 1 plus omega naught by 2 is the frequency of this coupled system, whereas this omega 1 minus omega naught by 2 times t, this is the beat uh, frequency. It's called beat frequency. And the time period for these two frequencies, so since time period is 2 pi by omega, so the couple pendulum time period for couple pendulum will be 2 pi by omega, means 2 times and this, so it will be 4 pi divided by omega 1 plus omega naught. And the time period for this beat frequency, this will be 4 pi divided by omega 1 minus omega 0. So couple pendulum. Just oh. So what we were discussing, the frequencies will be like this. Okay, now the time period, we know omega naught is the frequency of first pendulum, and the time period for it will be frequency time period, since it is 2 pi by omega naught, thus TC and TB values will be these. Now for the another pendulum, the time period will be 2 pi omega 1, and the TC value will be here. The derivations you can check from the lecture video. We are just discussing the result, right? Up to T1 divided by T0 minus T1. And the degree of coupling between these two pendulums is given by this expression, omega 1 square minus omega naught square divided by omega 1 square plus omega naught square, which will give us T naught square minus T1 square divided by T naught square plus T1 square. Okay. So I have a diagram here to show what exactly happens when there is resonance condition. So in resonance condition, what we do is, this is one pendulum, this is another pendulum, and they are coupled, right, using the spring. So in earlier two cases what we were discussing, like in first case we discussed in phase mode, that is we displace both the pendulums in same direction by same amount of displacement, then they are called in phase mode, right? And here the equation is just simple harmonic motion, they'll keep on oscillating like a simple pendulum. When we do out of phase mode displacement, that they are displaced by same amount but in opposite direction, then they are called out of phase mode. And here the contribution in frequency is also because of this spring. So these two were called normal modes. Apart from this, what happens when we make the displacement only of for the one at one time, say at time like I start this, I don't displace at all, I only displace this one by some value y and release, because when I'll take it to right, there will be restoring force acting in opposite direction, and it will usually, it used to damp, right? But since here the systems are coupled, when this its energy will start, when it will start slowing down, its energy will be transferred or exchanged to the this. Initially it was at rest, I only displaced this one, but after some time you will see that this one also starts moving, and there will be a time when this will be oscillating with maximum amplitude, and this one will come to rest, and after that again the energy whatever is here in this pendulum 1 will start going to pendulum 2, and this will keep on happening until if the damping is there, that is another case, but this exchange keeps on going between these two. This is the condition of resonance that we are discussing. So when this happens, as I said, one mass, one pendulum is at rest, I only displace another one. In this situation, this resonance happens, and this actually is the graph showing, like say if this blue one, what it's showing is actually, if I don't keep the frequency this much, what we want to show, the amplitude versus time. So initially, like I take it away from its equilibrium position, right? So its displacement is some maximum value. After that it will decrease, and because of damping also it may decrease, but I mean this is what happens. Initially this was at 0, after some time it will start increasing. So when we overlap these two equations, we see that when, let's call it 1 and 2 pendulum. So when pendulum 1 has maximum amplitude, pendulum 2 has minimum amplitude, minimum displacement. But at some point they both are displaced, they both have some amplitude, and then there is a situation after some time when all the maximum amplitude is in pendulum 2 and pendulum 1 is at static, and this keeps on happening. What this shows is there is energy exchange happening from this one pendulum system to another pendulum system because they are coupled, and this particular condition is of resonance. Okay, so this was the experiment that was performed. Now we'll discuss the another experiment, that is compound pendulum. So let's first understand what is compound pendulum. So in simple pendulum, as again I just tell, in simple pendulum we have a bob or some sort of mass which we hang using a thread or a string, which basically we call it's massless. If we are considering it's massless or its mass is almost negligible, that means all the mass is at this end of the string, and when the motion is happening, it's happening, this is the point of suspension, but the mass is only at this end of this pendulum. But when we talk about compound pendulum, it's a system. Okay, I'll read this out. It's a system where a rigid body which can swing in a vertical plane about some axis, says this is that axis we are talking about, passing through it is called a compound pendulum. So when a rigid body, here that rigid body is this rod with some holes in it, and it's swinging about this point of suspension. What is different here than simple pendulum? The different thing here is that here the mass is not at one end, right? The mass is throughout, the mass is extended throughout this throughout this pendulum. Here the mass was at the end of this pendulum system, here the mass is extended throughout, and now it's oscillating, so there will be something new happening here. First, let's understand this properly, what do we mean by center of mass. We had discussed this earlier when we were talking about calculating moment of inertia as well. So center of mass of a body or a system of particle is defined as a point at which the whole of the mass of body or the system of particle appears to be concentrated. We are not saying that actually that it is concentrated here, like for say I have a rod, cylindrical rod, okay, of course it's made of some material, and if I'm saying its mass is m, means it's throughout from this end to this end the mass is distributed, say its length is L, then we can talk about mass per unit length, but every point has some mass. But still, when we talk about center of mass, we say that it is a point in this rod where we can assume, or we can say that all the mass of this rod is concentrated. And how do we find that actually? If I give you example, if you put a finger and try to balance a small scale or rod, right, then you know that there will be a point where you will be able to, where you will be able to balance this scale or rod. That point is what we consider that all the mass is situated there, and that's why we are able to hold it from that particular position. This is what if we try to explain, this is the point in that body which is defined as center of mass. Similarly, center of gravity is also a term. Most of the time they are used interchangeably, because that center of gravity is a point in the system or in the body from where the force of gravity acts on the system, and that's why most of the time, if the gravity is same, then this point of center of mass and center of gravity are coincident. They are at the same position, so we can use both of these terms interchangeably, that's fine. So what we understand is the mass is extended throughout these kind of bodies, but there is one point where we can assume, we can say that all the mass can be considered that it's concentrated at that particular position, and the force or anything acting on it, we can safely assume that it's by considering that it's acting at that particular position, and we'll see now that how it works. Okay, we'll need to understand radius of gyration also for this, but okay, first let me tell, again let's consider simple pendulum case. As we said, mass is at the end of the string only, because we are considering the string is massless. Here, what is the effective length? The effective length that we talk about, because the time period also depends on the length, right? So effective length in case of a simple pendulum is this distance. If you will take the center of this bob and the point of suspension, this length, if I denote it by small l, and this length is what is the effective length in case of simple pendulum. Then what will be effective length in case of compound pendulum? So here, since all the mass was concentrated here, that definition was also correct. The center of, the distance from center of mass, actually effective length, we define the distance from center of mass to the point of suspension. This is called effective length. If you see this compound pendulum here, this is metal, not rod but metal scale kind of thing. So at the center we will think, this is a metallic scale, for it also the center of mass will be somewhere at the center, and then this is the point of suspension. This extended body or this scale is suspended by this particular point, which is called point of suspension or suspension point. So if we are defining effective length is the distance from this point of suspension to center of mass, then we may think that here also this whole length is L, that means this half will be L by 2. And if this is somewhere here, this point of suspension, then we may think that effective length here also is the distance between point of suspension and center of mass. But that is not correct. This is not the effective length. This is not the effective length for compound pendulum. Then we need to understand what is that. So to understand this thing, let's understand what is radius of gyration. Radius of gyration is defined as the imaginary distance from the centroid at which the area of cross section is imagined to be focused at a point in order to obtain the same moment of inertia. It can also be defined as the root mean square distance of various particles of the body from the axis of rotation. Radius of gyration is the distance where, if we assume that the object is, if we assume that at that particular point in this body, if we assume the all the mass is concentrated, then we can treat it as like a simple pendulum with all the mass concentrated at that particular point. Later, okay, let's try to derive, then maybe it will become clear. So that point is called radius of gyration, and we simply define it like moment of inertia, we denote I, and the relation between radius of gyration and moment of inertia is mass times k square. This is radius of gyration. This is the relation between moment of inertia of a body and radius of gyration. Okay. Now moment of inertia for a rod we may need, but okay. So for this compound pendulum, there are some holes in it. This is mainly just to vary the point of suspension. If we hang from here, because center of mass is same, or center of gravity, whatever you want to call, center of mass or center of gravity, the point of suspension we can vary depending on whatever other distance of holes we have, but the length and the, like if this is the point of suspension, we can call this some length small l, but again remember this is not the effective length that we need. So what happens is, let's explain. Yeah, do I have? Yeah. For any kind of irregular body, let's consider I have a body of some not so regular or symmetric shape, but this is some kind of body, and this is the point of suspension. It's suspended on a horizontal thing. This is the point of suspension. Let's call it P, and we know that it has some, of course, center of mass. Array. What's happening? Somewhere it will have the center of mass where we can assume that all its mass is concentrated. Let's call this point G, center of gravity. And the distance between these two points, we are calling it small l. Now, if I have suspended it about like from this point, and we are trying to displace it so that it will do oscillation about this equilibrium position. Okay, so I have displaced it here and it will start oscillating. So when it will start oscillating, you know this, there will be force acting on this body. So if this is the center of mass, this is the center of mass, and we are considering all the mass concentrated here. So like the way we treat simple pendulum, right, that since the mass is there, so we check that if mg is acting on it, there will be, and theta is the displacement, then we resolve it into components. The same way for this point we can safely do, because this is the center of mass or center of gravity for this particular body. That means there is mg force due to its weight acting downwards, and when we resolve it, this is theta, right? This is theta. When we resolve it into these two components, this will be mg cos theta, and perpendicular to this will be the component mg sin theta. Okay, now this mg, so the torque acting on this body, when we are making it to displace, we know there will be restoring force bringing it back towards the equilibrium position. That restoring force tau will be, like we know it's mass times acceleration, right? Here that for rotational motion we know that equivalent of mass is moment of inertia, and the equivalent of linear acceleration is angular acceleration, which will be here d2 theta by dt square. So this is the restoring force. this restoring force will be, as you see, mg sine theta. Mg sine theta means sine theta here, if you check sine theta, when theta is very small, we can consider sine theta, if theta is very small, to be theta. And if you take this triangle, then sine theta is p perpendicular by hypotenuse, right? So it will be x by L. It will be given by x by L. Anyways, okay. Should be okay. Just wait. Before I do, for small theta, theta will be this, and the equation of motion, this will be minus mgl sine theta, mgl sine theta, because we know, right, I mean, force times restoring force, sorry, torque is what? Torque we define as the force and the distance from point of suspension. So force here is mgl, sorry, mg sine theta is the force acting here. This is the restoring force acting here. And L is what? L is this distance from suspension to this. So this here is actually mg sine theta, and this is L, and since it's in opposite direction, that's why we get this expression minus mgl sine theta. When we solve this thing, or we rewrite this thing, we'll get, let me write directly, this again we can write at this, it's same, rotational angular acceleration plus mgl divided by I theta is equal to 0. This will be the final equation we'll get, where this mgl by I will be the angular frequency of this rotation. As you can see, this is also simple harmonic motion, you can say. The same equation, double derivative, and this mgl by I will be the angular frequency here. Thus the time period will be 2 pi by omega. This, when you put the value of omega from there to here, you will get 2 pi, and reciprocal of this means an under root also I by mgl. So the time period for this kind of compound pendulum will be given by this moment of inertia and mgl. Okay, now this is the time period, value of time period. Now, as we were discussing about the effective length, what will be the length that we have to use in this formula? For simple pendulum, we know it's the distance from point of suspension to, is someone saying something? So what is that, how it is different for compound pendulum, because that we will be using while doing the experiment also, that what is that effective length value. So here we know that for if we have some rod kind of thing, from the center of mass, the axis passing through the center of mass of this kind of body, the moment of inertia, let's call it Ig, because it's passing through center of gravity. From parallel theorem, we know the moment of inertia from its one end it will be Ig plus the mass of this body and the distance between these two axes L. Then it will be a square of this. This will be the moment of inertia passing through this axis of rotation. Now putting this value here, we'll get time period will be equal to 2 pi under root, this I is Ig plus m square, and Ig is actually, as I told, the relation between radius of gyration and moment of inertia, right? This is the relation. So Ig is this mk square plus ml square. And I'll substitute this value of I here, and it's divided by mgl. Let me write the final way after doing just some division. The final expression will be this. Now if you compare, this is for this compound pendulum, this is for this compound pendulum. For simple pendulum we know, for simple pendulum time period is given by 2 pi under root this L by G, where this L is that effective length. If we compare these two expressions, what these tell is that effective length here, for the case of compound pendulum, the effective length is actually small l plus square of radius of gyration divided by this small l, where here the small l is the distance, if you see, from the point of suspension to the center of gravity or center of mass of the body, but the effective length is this expression. Whereas for simple pendulum, the effective length is simply the distance between the point of suspension to the mass. But in the situation when we are oscillating compound pendulum, the effective length changes. So we did this exercise to understand how the effective length for compound pendulum is different. Okay. So yeah. So now after we proceed this, the same exercise if we continue. I mean, these are the expressions for time period and this thing, but when we taking this further, this expression further, again let me take just to make it clear. So this expression that we obtained, that effective length for compound pendulum, this is effective length for compound pendulum. Okay, this we obtained is radius of gyration. It has contribution from radius of gyration as well as the distance between the point of suspension and the center of gravity point. From this I can rewrite as like this, a square is equal to 0, and I'll get two solutions because it's a quadratic equation. When we'll solve it, we'll get two values of L here, let's say L1 and L2. These will be the two solutions such that the capital L will be L1 plus L2. When we'll solve, we'll see they will set those two values of L will satisfy this and also will satisfy this. Okay, here the length of equivalent, this we know is the effective length. If all the masses are okay, now proceeding because we'll need it for our, so right, now we need to understand one more thing. What is center of oscillation? This exercise is actually needed to understand the experiment, which was measurement of acceleration due to gravity by compound pendulum and determination of radius of gyration about the axis through the gravity. So the experiment that was performed was oscillation of this compound pendulum, which was something like this. And since we know, we already obtained the time period expression, right? That time period is 2 pi under root I by mgl. So if we do this experiment, and what we change here, the center of gravity point will remain same, only this point of suspension we can change. We can increase the distance between point of suspension and center of gravity by using different holes for suspending this compound pendulum. So we'll keep on changing this small l, right? This actually is not correct. I mean, this x and l just ignore. What I'm telling you is this point of suspension and center of gravity is our small l. This is not correct for our case right now. And depending for the rod, we know from the center the moment of inertia is, for rod, whatever is its value depends. I mean, this is a metallic scale, it will be different. If it's a rod, it will be different. So whatever is its value, then we know what is the relation. If we want to find out moment of inertia here, that is the point of suspension. So what it means is, if we know the mass, we know this length, then we can, and time period we'll calculate. Like when we are performing this experiment and we give it some displacement, it starts oscillating, and we measure how many oscillations happen in 1 minute or something, then we'll find out the time period also, and I we can calculate. From this we can easily calculate the acceleration due to gravity. Okay, if you will rearrange, you will get this. If I will take square of this, and it will be t square divided by 4 pi, okay, t square divided by 4 pi, and this I will come here, this m and l will come in numerator. So it means the acceleration due to gravity will be 4 pi I by ml t square. So we'll be able to determine the acceleration due to gravity value of small g using this compound pendulum experiment, as well as we'll be able to determine radius of gyration about the axis through the center of gravity. So this is the experiment that was performed. Experiment again, you can go to the lectures to watch these things, and this is just I'm telling what the values we were trying to determine from this. So one thing we need to understand from here again is what okay, the center of oscillation I was talking about. So that we talked about how the experiment was performed. Now why we need this is the center of oscillation. I have not kept its definition. Okay, so center of oscillation is actually, if we take a irregular body, again, say this is the point of suspension, this is the center of gravity point, distance between them is small l again, then you know the effective length when we calculate, it's not the small l, it's somewhere else. Okay, and that effective length from the point of suspension, let's call it O. Okay, the distance between point of suspension and this point in the body, where if we think that all the mass is concentrated here, and we can then if we oscillate by putting force on this particular point of the body, we can assume it as a simple oscillation. So I mean, there's nothing more to get confused. It's just for a simple pendulum, we have all the mass concentrated at one end. In compound pendulum, the mass is extended throughout the body, but this center of oscillation is the point in the body which is away from the center of gravity of the body also, and this point of suspension also, but in such a way that if we assume all the mass to be concentrated there, then we can treat this body as same as this simple pendulum case. Okay, and this point is called center of oscillation point. And when this happens, if you will plot the graph between time period and say this is the distance in this direction, the distance between P and G are increasing. Say the distance between P and G is increasing, then the time period varies like this. Okay? It varies like this. And if you draw a line parallel, you'll see that, if I'll make it, you'll see that there are two positions of P, P1, P2, also P1 prime, P2 prime. It means there is such a point even when you're talking about this rod, right, metal scale that we have. Somewhere there is point of suspension, but there is some point from this G where this center of oscillation lies, and the time period is same for all these 4 points. I mean, there are 2 points on one side of this O, there is another point on other side of this, where the time period for all these distances comes out to be same. Yeah, okay. And so this is what was done in the experiment as well. Now moving on to solve the questions based on this. So this was the experiment about compound pendulum. Just me just a minute. Okay, so the first question, let's try solving. This is based on the compound pendulum, it seems. A thin uniform bar of length 60 centimeter. So length we have been given. The length is 60 centimeter. The length is 60 centimeter. Is made to oscillate about an axis through its one end. There is a bar. The point of suspension is at its one end, and we need to find the period of oscillation. The length, say some length, it is 60 centimeter, and we need to find out the time period of oscillation. Now we know time period of oscillation for a compound pendulum, the expression is 2 pi under root moment of inertia. Now, or in terms of radius of gyration, if I'll write, it will come out to be k square by L plus L, where the small l is what? Again, I'll repeat, the small l is the distance between the center of gravity of this bar and the point of suspension. So if the total length we have been given, the total length is 60, then this will be 30, right? The small l will be 30 centimeter. So this divided by small g. Now if we need to find out the value of radius of gyration, and as I told, the relation between moment of inertia and radius of gyration is this. So first we will find out the value of moment of inertia, then we will find out the value of radius of gyration here. So since for this kind of uniform bar, we know for a uniform bar means like uniform rod. The moment of inertia for the about the axis passing through its center of gravity, it is given by 1 by 12. If the mass of the body is m, then m, and the total length is l square, then l. So here we need to find out this. Okay, so I mean mass we know, length we know, but okay, what we need to find out here is actually this k. K is, from here we can see I is mk square, so k square will be I over m. This I is actually this g, ig over m. That means 1 by 12 ml square, I'll divide by m, then it will be l square by 12. When I'll calculate, L is 60, so 60 square divided by 12, this will be, let me use my calculator, this will be 60 times 60 divided by 12, this will be 300. I'm getting. Radius of gyration value will be 300 centimeter square because the length is in centimeter. Now using this value of k here, 2 pi and k square, okay, so this is k square. I didn't take the root because we will use it here. This will be 300 and the small l is 30 plus 30 divided by, it's given, we can take, I mean this is the value. In SI unit it is 9.8, here it will be 980 centimeter per second square. When we will solve this, this will be 10, 30 plus 10, 40 divided by 980, let me calculate this, 40 divided by 980 and root of this 0.408, it will be 0.201 times 2 times 5 will be 1.269. So time period, after calculating I am getting time period is 1.269 and something. If I'll keep up to 2 decimal, it will be 1.27 seconds. So the best matching answer will be this 1.225 seconds. Sometimes this difference happens because of the value of pi, up to which decimal point we are taking, but the best matching answer here will be option B. Okay, so next question is, if the mass of object is doubled, then what will be the effect of time period of a compound pendulum? So for a compound pendulum, again recalling, time period is given by 2 pi under root I over mgl. Here the question is, if the mass of object is doubled, if the mass becomes double, then what will be the effect of time period? From this expression we clearly see the dependence of time period on mass is 1 over root m, and if this become doubles, then how will the time period change? So this was earlier, this means it has reduced by 1 over root 2, right? What we see here is t prime is actually 1 over root 2, I mean still this 1 over root 2 and 1 over root m, so anyway this was the time period of earlier case. So this new time period will reduce by 1 over root 2 factor. This is the correct answer. Next question is, if the mass or if the moment of inertia of the object is increased to 4 times, then what will be the effect of time period of the compound pendulum? Moment of inertia. Okay, so since again time period is 2 pi and under root it's I mgl, then if the moment of inertia is increased by 4 times, I'll just keep this the same. Moment of inertia now becomes 4 times. Then if we compare these things, this means if I'll take 4, root of 4 means 2. 2 times 2 pi under root I over mgl, and this whole thing is what? This whole thing is the old time period. That means 2 times t. This means the new time period will be double. This new time period will be, if the moment of inertia is increased 4 times, then time period will become double. The next question, calculate the time period of an object having mass, moment of inertia. We have been given moment of inertia 100 kg meter square. Mass of the compound or this object is 10 kg. Okay, and center of gravity lies at the point below the point of suspension. So we have not been told how this object is, how does it look like, maybe something, anything, but the point of suspension and center of gravity, the distance we have been given, that is the small l we have been given, which is 20 centimeter, and we have been asked to calculate the time period. The time period, if I write in terms of radius of gyration, then it will be k square by L. Do we need that? But I don't need to convert it into radius of gyration. Directly moment of inertia is given, so I'll again just keep it in this form. Okay, I'll just substitute these values. Moment of inertia is 100 divided, okay, so mass is 10. This G will take 9.8, and this length, to keep everything in SI unit, I'll convert it into meters. 20 centimeter means 0. Centimeter, yeah, it will be 0.2 meters. 0.2. This everything should be under the square root sign. And now when I'll calculate this, it will be, okay, let me do 9.8 times 10 times 0.2, 19.6, so 100 divided by 19.6, 5.1020, 5.1020. Root will be, so under root, when I solve this, I'll get 2.25876. When I'll multiply, it will be 14.19. I'm getting the value 14.19 second. Again, the best matching value here, if I although even if I take the round off, as we have earlier discussed rounding off how it works, it will become 14.2 second. But here the best matching answer will be this. Just to remind you again, sometime because of how much precise value of pi we are taking, that may be changing this or something. Or if you take this G value, instead of 9.8, you take it to be 10, then also the answer may change a little bit. But the best matching answer here will be 14.1. You can try with making it 10 also, and then we can check. So this is the time period for this. Next question is the distance of point of a compound pendulum from its center of gravity. Again, let's draw for clarity. We have not been told how the shape is, so just something random. The center of gravity, say its center of gravity is here. The time period of oscillation and the distance, distance of point of a compound pendulum from its center of gravity. This distance of point, I think it's point of suspension. Okay. distance of point of suspension of a compound pendulum from its center of gravity is small l. The time period of oscillation relative to this point is capital T. If g is equal to pi square, then the relation between this length and time period will be what? We need to find out the relation in this form. So first of all, again, what is the time period? The time period is given by moment of inertia and this expression mgl. Now in terms of radius of gyration, again we don't need to derive it, we already know. In terms of radius of gyration, we can write it as k square by l plus l divided by g. This is also, this whole thing is under the root. This is another form of time period when we know the radius of gyration directly. Now we have been given if g is equal to pi square. So if g is equal to pi square, if I'll put the value here, g is equal to pi square, then root of pi square will be pi. So this pi will be cancelled and I'll get something like this, k square by l plus l. Now to get it in form of this equation, I'll take square on both the sides. Okay, when I'll take square on both the sides, it will become t square 4 and this expression will remain like this. Okay, t square, I'll take it here in the denominator, then I'll get k square by l plus l. Okay, now I'll rewrite this something as this, k square by l plus l square by l, right? This is the same, and then this l will come to numerator side, on the left hand side I mean, then it will be t square by 4 times l is equal to k square plus l square. Hope I'm not making some mistake. Again rewriting this, it will be l square minus, when this will come on the right hand side, it will be minus t square by 4 times l, and this k square is already on right hand side, so it's alright. So the relation between small l and this time period is this. Now where is it? L square minus t square by 4 l plus k. So yeah, so the first equation is the correct thing. Now the next thing is, okay, so it's about waves. When we talked about the center of when we talked about simple harmonic motion last time, we discussed that it is there is motion of particle or the system about equilibrium position periodically, and then we call it simple harmonic motion. In simple harmonic motion also, okay, I'll tell how waves we get. So like if you know what is a slinky, so it's a spring kind of thing, right? It's very flexible. It is kind of spring, but these loops are of bigger radius and they are very flexible material. So we can easily bend it and expand it, compress it. So this is called slinky. Metallic, it could be made of plastic or something. So say if you two of friends, one friend is holding one end of the slinky, another friend is holding another end, and they are making it move in this way, as you can see in this particular diagram. Here, if just say another person is just holding it, he is not moving, this one person starts pushing it up and down, then this gets displaced in this direction, and up and down it starts going like this. Here the so this transverse wave thing, this is called transverse wave because the motion, I mean the particles, like the particle here is going up and after some time it will come down, but this wave is moving in towards this right direction of wave is towards right, but at every point this slinky ring, okay, its motion is only up and down. At every point you can see its motion is only up and down, but overall the wave or the motion is happening in perpendicular direction. In this kind of situation, this kind of wave is called transverse wave. Okay, when we see this wave is created, the maximum displacement of particle is called the amplitude. I mean at any point there is different value of displacement. The maximum is shown here. This is the maximum on another side. This is called crest, this is called trough. And if from any point, because you can see it's periodic, right, the displacement starts from 0, it becomes maximum, it becomes 0, it goes to maximum on another side, and after that it will again become to 0. So this one same thing, and after that it starts rotating, I mean if it starts repeating again. This is called wavelength. From any point to another point where this behavior starts repeating, that is called the wavelength of the wave. So either you can take from here to here, or from the maximum to maximum, or from this point to wherever you will see, this will show the wavelength of the wave. So this is transverse wave. Now the same slinky, if again those two friends, one is holding, another one is holding one end, and they start moving towards each other, then the slinky will get compressed, or if they start moving away from each other, the slinky will get expanded, right? In this case, the bodies will be, instead of, now they will not be moving up and down. You see the same slinky, if you expand or compress, now the particles are moving in this or this direction, and the wave also is moving in the same direction. In this kind of wave, this kind of wave is called longitudinal wave, when the waves, where the displacement of the medium or the particle is in the same direction as the direction of traveling wave. So here the particle is moving to and forth, and the wave, overall wave is also traveling in this direction, then it's called a longitudinal wave. And where when all in this kind of spring or slinky example, when all the particles come compress, it's called compressed area. When they are apart, it's called rarefaction area. And like here, this crest and trough were repeating. In longitudinal wave, this compression rarefaction is repeated. So these are the two kind of waves. Now when we have a system of a tightly tied string, okay, and if it's fixed at both the ends, and you push it little bit or pick this a little bit, so that there is some displacement of this, right, this will become a wave, go towards this end. Now because this end is closed, it will come back, it depends in it will come out of phase or in phase, but it will reflect after traveling in this direction. This wave will reflect from this fixed end and come back. And when this kind of situation happens, that there are two different traveling waves, either they are in same direction, or they are in, maybe one is going in this direction, another one is coming in this direction, there is some different kind of standing waves generated. So standing wave is what? Standing wave is combination of two waves moving in opposite direction but having same amplitude and frequency. So when the both ends are fixed and we have a string like this, then if I create disturbance at one end, it will travel to the other end and then it will be reflected. So in this case, what's happening, if I'm continuously generating disturbance at this point, then one wave is traveling in right direction and another wave is reflecting back and coming to left direction. So what's happening, both the waves have same amplitude as you can see in the diagram, and their frequency is also same. Yeah, so frequency, amplitude, like I told, it's repetition. You can see this when the length after which this behavior starts repeating, it's called wavelength. Now the frequency means how many these cycles happen per second. You already know time period and frequency. Okay. So when these two traveling waves are of same amplitude and same frequency but in opposite direction, this is called, they make actually standing wave. So how this standing wave look like, it's you see it's initially tight rope, it's not loose, but when you give it some frequency, either you see very small actually, either up or either down, some oscillation, as you have seen in experiment. The professor had demonstrated very nice experiment for this. When you see something like this, here the length of the string is L, right, and you see this is half cycle. If I call this is the complete cycle, then you can clearly see this is half cycle. So this is called, this is one more thing. Here you can see that the particle has, here you can see the particle displacement is 0. Here the displacement of particle is maximum. This point is called node, this point is called antinode. Again, here the particle in both the direction, any direction for this red curve, here the displacement here is maximum, this is called antinode, and here for this particle the displacement is 0, this is called antinode. So these troughs and crests are also called, when for standing wave, because here these two waves are combining, so here the displacement is maximum, it is called antinode. Here the displacement is 0, it's called node. So we'll see there are different nodes we get. We'll see what is n, but we may, if we give frequency to this kind of string system, we may see something like this, or we may see something like this. The vibration, we'll see something like this. Okay, anyways, so we'll see how we get this. So for traveling wave, we know traveling wave equation, right? Traveling wave equation will be y is equal to a sine kx minus omega t, where a is the amplitude, k is 2 pi by lambda, and omega is 2 pi by time period. Stationary wave, okay, so the derivations again you should look in the lectures where the professor has explained these. So for this one equation going in right direction, we'll write one, say a sine kx minus omega t. Now the coming back equation, the equation for that, if we write in this one, it will be same, only it will be different in phase. Delta here is what I am showing us. It's representing the phase difference between these two waves. Now the total equation will be combination of this. When we will solve this, and there are some boundary conditions which for detail again you should go through the lecture video. So the boundary condition, I'll just tell. The boundary condition is that, see, this is the x distance, then at x is equal to 0, this is x is, this position is x is equal to 0, and this position is, if the length of string is L, then this is the position. So at this both point, the displacement in y direction is 0, right? Here also the displacement in particle is 0. in the y direction, here also displacement of particle in y direction is 0. So these we call boundary condition. These boundary condition are that at x is equal to 0 and x is equal to L, y is equal to 0. Okay, for this also y is equal to 0. Using these boundary conditions, when we solve this equation, what we get is, I'll directly go to the final result out of this. Just a minute, I need one more slide. Okay, so the final result after solving this equation that we get is that, or I'll put the value from first boundary condition. Actually, from first boundary condition we get y is equal to 2a sine kx cos omega t. In this, when we put the second boundary condition, which was x is equal to, at x is equal to L, y is again 0. When we put here the x is equal to L, then y is 0 means it will be 2a sine k, x I am keeping L, cos omega t, right? If this side is 0, we know, this will equate something this, because this is a constant here. We are only substituting the value of this. Cos omega t is constant, 2a is constant. That means sin kl is becoming 0, and that's why y is becoming 0, because the other thing 2a and cos omega t are 0. So from this we understand that ultimately sin kl is what is becoming 0, and we know that sin value is 0 for pi, 2 pi, or sin pi, 2 pi, 3 pi. So it's sin, okay, so sin is 0 when kl is integral multiple of pi, where n can be 1, 2, 3 and so on, right? From this is integer, n is integer here. So the value of L from this expression will be, if wait, I'll put the value of k. K is 2 pi by lambda n pi, pi cancel. From this L will be lambda n by 2. As I showed here, so L, if the length of the string is this, and we said the L relation between the length of the string or wave is, and wavelength is given by this, that is L is equal to n lambda by 2, means its integral multiple of the wavelength. Then this is, we call nodes. For n is equal to 1, this is half the wavelength. You can see, if we call this is 1 wavelength, then we can clearly see this is half wavelength. And if you put the value n is equal to 1 here, you will see this L will be equal to lambda by 2, that is half wavelength. And this is n is equal to 2, that is, you will put 2, then 2 will be cancelled, this length will be equal to this 1 wavelength. We can clearly see that is correct. So this n here is the node, and this relation we have obtained. So this tells that the length of this string is integral multiple of wavelength, where n is equal to 1, n is equal to 2 are the modes. Now this n is equal to 1, actually it is called fundamental mode. It is called fundamental mode, and n is equal to 1 is called fundamental mode, and for n is equal to 1, L we get lambda by 2. Now we want to find out what will be the frequency for fundamental mode. We know velocity is product of frequency and wavelength, right? Now, uh, this lambda value will get from this. So, and there's the, okay, one more thing. Okay. So the frequency from this will be velocity of the traveling wave divided by wavelength of the wave. So velocity divided by lambda value I'll take from here, that is 2L. 2L. Also it is known that velocity for the string wave traveling is given by T over M, where T is the tension in the string. Putting that value here, I'll get 2L under root T by M. So from this clearly we see that this I'm denoting as 1 because it's fundamental mode. So frequency for fundamental mode what we mean, n is equal to 1 means the standing wave generated is this lambda by 2. This is fundamental mode, and the frequency here is given by 1 over 2L, where L is the length of this string, and tension in the string divided by mass per unit length. Here the mass is what? This mass is mass per unit length of the string. Okay, this is mass per unit length of string or rope or whatever that thing is. So this is the formula, frequency of fundamental mode. Similar way, n is equal to 2, n is equal to 3 we can calculate. Like n is equal to 1 is fundamental mode, n is equal to 2 is called overtone, first overtone, n is equal to 3 is called second overtone. So these are, and how their values changes. For n is equal to 2, the frequency will be 2 times the frequency of 1. Okay, this is the relation. Now the experiments, again for the experiments you should refer to the videos, but what we were trying to find out was to determine the phase velocity. Like, okay, so here we can see if we are able to, when we do, okay, sorry, let me explain. So the experiment is to determine the phase velocity of stationary wave produced in a string. For this experiment we had a string and the two ends, one end was tied, another end we had given it tension by suspending a mass to another end of the string. So, and after that we were giving it some frequency disturbance to this tight string. Because of that there will be standing wave generated, and that standing wave will have some vibrational frequency given by this expression, right? Now if we know the frequency, because we know the mass of the rope, we know the length of the rope, we will calculate mass per unit length. Same way the tension we will calculate, because the tension value will depend on the mass that we are hanging and the G value. So that mass what we are changing will keep on changing, so the tension will change. Depending on the change in tension, the frequencies will change, and using the relation between velocity and lambda we will see, I mean depending on what frequency I am giving, there will be a number of modes, different number of modes will be generated. From number of modes I'll find out the wavelength value, frequency I know what I am giving, from that I'll calculate the phase velocity. So this was the one experiment. The another experiment was on longitudinal wave in air column. Here also the same expression we were using, and here we were creating the disturbance. Here the frequency dependence, this relation we were using, it's something like this, right? So we will change the air, I mean you can see the experiment. there was water in a cylindrical tube, and there was hollow cylinder that we insert in this, and then using a tuning fork, when we were hitting tuning fork at a surface, it starts vibrating. Every tuning fork has particular frequency with which it vibrates. When we bring that tuning force near this one end of this open pipe, then and we move it away and near this to get where the maximum sound I'll be getting. So depending on where I'm getting the maximum sound, I'll adjust the height of this open pipe in this water thing, and from there I'll get that length where the maximum sound is coming, and depending from this again we can calculate the frequency and then velocity of air. Thus what we are calculating ultimately will be velocity of sound waves. So this was the another experiment. So again we don't need to go in detail because we are focusing on the assignment. So for this experiment detail, please check out the lecture video. So moving towards the question now. So first question is, the frequency of the note produced by plucking a given string increases. The frequency increases by plucking a given string. So we know the relation of frequency. This frequency is given by 1 over 2L under root T by M. If so frequency will increase when length of the string increase. You see, length is inversely proportional. That means if length increases, then frequency will decrease. So this is not the correct option. The tension in the string increases. When the tension of the string increases, of course there will be increase in the frequency. So this is the correct option. And then let's see other option also. If tension decreases, frequency is directly proportional to the tension. That means frequency will also decrease. Mass per unit length of the string increases. If mass per unit length of the string increases, it's in denominator, means it's inversely proportional. So if this increases, then again the frequency will decrease. So the only correct option here is this, that the frequency of note produced by plucking a given string increases when tension in the string increases. This is the correct option. Now the next question. In stationary waves, energy is uniformly distributed. Energy is uniformly distributed. Okay, we need to find out what is the correct answer. In stationary wave, we know when we get stationary wave, when two traveling wave of same amplitude and same frequency, and they are traveling in opposite direction, then we get this standing wave. Okay, energy is uniformly distributed. Energy, you can see where the displacement is happening, the particle will have some energy, right? Here the particle is not doing any displacement. Okay, that means there is no energy. That clearly shows that throughout this standing wave the energy is not uniform. The next is, energy is zero at nodes and maximum at antinodes. So you know where the displacement of particle is zero, this point is called node, and here where the displacement is maximum for the particle, this position is called antinode, as we had discussed some time ago. So what's the statement, energy is zero at node? Yes, the displacement is zero, means the energy is zero here, and energy is maximum at antinode. Here the displacement is maximum, means energy is maximum. So this is the correct statement about the energy in stationary wave. Energy is maximum at node? No, energy is zero actually at node. Energy, these are also not correct statements. The only correct statement is B. B is the correct answer. Now the next question, if the string is in its fundamental mode of vibration, then velocity is inversely proportional to fundamental mode. Fundamental mode means n is equal to 1 condition, right? For that, frequency is equal to 1 over 2L under root T by m. And we have been asked velocity when it's when frequency is in fundamental mode, then velocity is inversely proportional to. When frequency is like this, so velocity will be what? Velocity is equal to n lambda, and lambda, wait, was something, okay. For n is equal to 1 mode, we know that n is equal to 1 mode means lambda is for n is equal to 1 mode, lambda is 2L, right? Because n is equal to 1 mode means this, just up and down, I mean this kind of standing wave happens. This is L and this is half wavelength. So for n is equal to 1, the lambda is 2L. Oh sorry, this is actually, I'm calling frequency also n. This is the frequency actually, sorry, I'm calling it n. N is mode, let's keep that symbol separate, and frequency let's keep as nu. Okay, frequency we can call it 1 because it's fundamental. So since velocity is product of frequency and wavelength, here wavelength clearly is 2 times L, and frequency value, when I'll substitute, I'll get 1 over 2L under root T by m times 2L. So 2L will get cancelled, I'll be left with this. This is the expression for velocity in fundamental mode. That means the correct statement is that velocity is inversely proportional to the mass, square root of mass. So square root of this linear mass density means mass per unit length. This linear mass density means mass per unit length, which is small m. So square root of this is the correct answer. Okay. So next question is the fundamental frequency of a string stretched with a weight of 1 kg is 512 Hz. The weight required to produce its octave. Again, fundamental frequency. That means nu is equal to 1 over 2L under root tension and this mass per unit length. Then the question is, with 1 kg weight, we are generating fundamental frequency of 512 Hz. Then how much weight is required to produce its octave? When we say octave, we mean the double of this particular frequency. If we are using 1 kg to make fundamental frequency of 512 Hz, then to make its octave means this octave will have the frequency double of this fundamental frequency. So to generate a standing wave of this frequency, the question is how much weight is required. Since what are we doing by this weight? When we give this weight m times g is giving us the tension, right? We can clearly see that frequency is proportional to tension. That means it's proportional to this weight that we are providing, right? That means to make this frequency value double of fundamental frequency or 512 Hz here, how will it become double? How will it become double? Is when this mass, G is anyway constant, this mass becomes 4 times, then square root of 4 will be 2. That means if the mass becomes 4 times, then the frequency will become double, that is we'll be able to generate the octave. So if the mass was 1, so 4 times the mass will be 4 kg weight. This is the correct answer. So this using this relation we can, without doing any calculation, we can, by understanding, we can find out the value should be 4 kg. Okay, next question is, a string of length 100 centimeter is clamped at two ends, and okay, the clamping is actually just a minute. The clamping we have not, it's not been shown, but okay. So these ends A and B, these two strings have been clamped, and the length of string, that is this total length, okay, this total length is this capital L. And how many wavelength you see here? This is one wavelength, right? This is second wavelength, and this is half. That means this total length is actually 2.5 wavelength, that means 2.5 lambda. And relation we know between, so L is given by n lambda by 2, right? When we equate these two, 2.5 lambda, we can clearly see, if we compare here, this implies n is equal to 5, and we can see also this is 1 2 3 4 5, this is n is equal to 5 mode. Okay, now using this, what we need to calculate is the tension in the string we have been given, mass per unit length value we have been given 0.0001 kg per meter, the frequency of vibration of the string. So for fundamental mode, we know that the frequency is this. Okay, this is for n is equal to 1. Here n is not 1, here n is 5. So what is the relation? In general, okay, in general, for n mode, the frequency is n times this fundamental mode. That means if I want to find out the frequency of vibration for fifth mode, this will be 5 times the fundamental frequency. Now to calculate this, I'll put this value here. T is 4, mass per unit length is 0.0001 kg per meter. When I solve this, let me solve this thing using calculator. I'm doing this calculation using calculator, other things are just easier. Or yeah, this 4 square root will be 2, so 2 and 2 will be cancelled, so 5 divided by 4. Okay, but I need scientific calculator. Oh no, actually this will be 5 by pi. You're right. And this will be 10 to the power minus 2. Oh, sorry. This is not pi in this formula. This is capital L. I'm very sorry. This is capital L in the formula. The frequency formula is this. So this L, we have been given L. Okay, what is the value of L? 2.5. The L value, okay, the L value is here, 100 centimeter. By taking it in meter, I can write it as 1. So this will be, this is L, and the length is 100 centimeter, that is 1 meter. Okay, so now this value will become 5 times 10 to the power 2 hertz. That means 500 hertz. Yeah, I'm very sorry, this I did blunder here. So the correct answer will be 500 hertz. Now the next question. The ratio of intensity of two superposing waves is 4 is to 9, the ratio between the maximum and minimum amplitude what will be? So we should know this, that intensity is actually uh, square of modulus of the amplitude. So we have been given, let's ratio of intensity of two superposing waves. Let's call the intensity of one wave as I1, another wave as I2. Then their ratio we have been given is 4 by 9. Okay. Then since we know this thing, so amplitude of first one, square of it, amplitude of second one, and square of it. And then so from this relation I'll find out that A1 and A2, the values will be square root of 4 by 9, that is 2 by 3. So A1 ratio of A1 to A2 is 2 by 3. Now we have been asked the ratio between maximum and minimum amplitude of resultant wave. So when these two different waves of amplitude A1 and A2 will superimpose, the maximum amplitude they will get is A1 plus A2. This will be the maximum amplitude. This will be maximum amplitude. And the minimum amplitude will be A1 minus A2. This will be maximum amplitude, this will be minimum amplitude. Now the okay, now we need to take the ratio of this A1 plus A2 mod of this and A1 minus A2 mod of this. So A1 plus A2, wait, let me divide it to, because we don't know the value of A1 but we know the relation between them. So if I divide the numerator by A2, I'll get A1 by A2 plus 1, right? And here if I divide by A2, I'll get A1 by A2 minus 1 and mod. Now A1 by A2 I know, it's 2 by 3. That means 2 by 3 plus 1 divided by 2 by 3 minus 1 and mod of this, sorry. Yeah. So mod of this. So the value will be 2 by 3 plus 1 means 5 by 3, and here 2 by 3 minus 1 means minus 1 by 3, and mod we are taking, so it will be 1 by 3. So this will be 5 by 3 times 3, cancel, ratio will be 5 by 1. So the correct answer is D. Okay. Now next question. The wavelength of a progressive wave is 60 centimeter. There is a wave progressing in some particular direction, so it's a traveling wave with wavelength 60 centimeter. What is the shortest distance between two points separated by 30-degree phase difference? Phase difference, we know the relation between phase difference and wavelength is 2 pi x by lambda. Okay, here phase, we have been told phase difference is 30 degree. 30 degree in radian I can write as pi by 6, and since we know phi is 2 pi x by lambda, so from here I'll get the value of x is equal to lambda by 6, and the 2 will come here, means lambda by 12, and since the wavelength is 60, this distance between these 2 points, so that the separation in phase is 30 degree, we were asked to find out, so the distance between these 2 points will be 5 centimeter. This is the correct answer, 5 centimeter. Okay. Now next question is, okay, so these were the questions based on this standing wave. Now there is another experiment that was shown in lecture video for this week. which was based on linear expansion of metal. So we know when we heat material, it expands. This we know in general. When we give heat, it expands because the particles become energetic and they start moving with more energy, and there is expansion in the material. When we talk about linear expansion of metal, so for metallic rod as shown in diagram, which at some particular temperature, say its length is L, and after heating at some higher temperature its length increases, okay, then this increase in the length, that is this change in the length of this metal rod is known to be proportional to its original length, and it is also known to be proportional to the temperature difference, okay. Thus the relation we know is that the change in length, combining these two, we know the change in length is proportional to the original length and the change in temperature. So this temperature so at T naught, at some T naught temperature, length was L naught, and at T temperature the length is becoming L. So the change in length, and this T is actually T is T minus T naught. It's either we can write delta T or small t, that's fine. So this is the relation, and if I replace this proportionality sign, then I'll need to put some constant. That constant is actually called alpha. Don't confuse, this is a proportionality sign, but this is alpha. This is a constant called linear expansion coefficient. It also depends on the material, and for a specific material in particular temperature range, its value we can say is constant. So this is the constant, and L naught T. So this is the dependence, and from this we can find out the value of linear expansion coefficient is actually 1 over L naught, and delta L by T you can say, or we can write dL by dt. I mean, the change is what basically we are trying to find out, okay. And the same thing in the experiment what the professor had demonstrated there, if you remember, so there was a metal rod kept, and there was a coil in the experiment setup which was surrounding this metal rod, and when we were giving current to this coil, there was heat generated. Because of heat, there was increase in the height of this rod, and then we had a micrometer set up at the top. So whatever, because this change is very small, it's in micrometer, so we had a micrometer to measure that change, and then we were measuring the change, and what we were finding out is that, so from this different temperature value we'll note down, and then at those different temperature the corresponding expansion, the change in length we'll note down. So what we'll obtain is, we'll obtain the change in length, and we'll also obtain the change in temperature. So when these two things we plot, okay, when these two things we plot, we get, sorry, this is linear, this straight line. When on y-axis, x-axis we plot these things, we get this thing when we plot this slope. Oh, it may not need to be passing through the center. Let me make the correct one. Okay, it may be something like this, but the slope of this graph will give us the value delta L by delta T, and using this we'll find out the value of linear coefficient, because original length we know, delta L delta T we experimentally are finding out, and then with this slope value we'll get this, we already know this. So we can always calculate alpha. We will perform this for different temperature, different expansions, and then taking average, we can say the thermal expansion coefficient for this particular material, whatever value we calculate. So this was the experiment, and this is the basic formula, working formula for this setup. Now let's try solve some questions. So first question is, a metal is calibrated at 0 degree centigrade. Its length at that temperature is 100 centimeter. So at 0 degree centigrade, the metal scale is 100 centimeter in length, and we have also been given alpha value, coefficient of linear expansion of metal, to be 20 times 10 to the power minus 6 per degree centigrade. This is the value of alpha. And the percentage error in measurement of length of, okay, so we need to find out the percentage error. Now since we know alpha is 1 over L naught, okay, delta L by, oh sorry, delta L, the change in length, change in temperature. So this, if I rewrite, because I want to find out the percentage error in measurement of length, so I'll write in terms of change in length. The change in length, if I'll write, it will become alpha L naught times change in temperature. Now the percentage error in this, okay, percentage error in this will be the percentage error in alpha, okay, when we are doing the calculation, the percentage error in this L naught, because it's I think fixed or something, so L naught is fixed, it will, there is no any error, we have just been given, then there will be this also will be 100. So the scale length at that particular temperature is 100. So L naught will not have any error. Then delta T by T into 100, right? So this will be delta alpha by alpha, sorry, the change into, we have been given the value of alpha, this is 20 into 10 to the power minus 6. Okay, I think okay, instead of doing it like this, I would suggest, okay, just forget this for time being. From this equation you can see alpha, and this is basically the change in this, right? So this will be alpha, and the dt, or change in temperature, times 100, just to make it less confusing here. Value of alpha is 20 times 10 to the power minus 6, and the change in temperature is 50 degrees centigrade, means 50, and then multiply it with 100. What will be this? 50 times 20,000, 10 to the power minus 6 plus 2, this means this will be 2 minus 6 means minus 4 and 3, 10 to the power minus 1, that means 1 over 10, means 0.1%, error will be 0.1%. Okay. Next question. The sides of cube are measured to be 100 centimeters. So we have a cube now. We have a cube. We know for cube the volume is like this, okay. Length we have been given, it is 100 centimeter at 0 degree centigrade. Now we need to find out this volume at 100 degree centigrade. At 100 degree centigrade we know there will be expansion, and because of that, if I got this as L naught, and there this volume will be this, and at higher temperature the uh, side will, there will be some other value, and based on that there will be some other volume. So what will be the value we need to calculate? So one way is we can do is that using the formula that this formula we know, right? Alpha is 1 over L naught, and there is change in length and there is change in temperature. From this from this delta L is alpha L naught this. So change in length means final minus initial, right? That means the final length is alpha L naught T plus L naught. When I'll take out L naught common, I'll get alpha T plus 1. So one thing is I can calculate this capital L. I know this, I know L naught value, which was 100 centimeter. Alpha value we have been given, and temperature difference is 100. So I can calculate L from this, and then I can take cube of that. That is one way. Another one way is there, which we need to know this also, that when a body which is when this is a cube, right, that means all sides are same. That means if linear expansion is happening for this side, the same linear expansion will happen for this side, the same linear expansion will happen for this side, length, width and height. When situation is like this, then as we know that length change in length is something like this, okay. From here what we find out, that the final length is original length times 1 plus alpha times the change in temperature, where alpha is the linear expansion coefficient. Based on same logic, it's known that when the linear expansion is same in all direction in the body, then volume, what will be the volume after expansion? We know the relation that it will be 1 plus some gamma T, where this gamma will be, since it's a volume and for volume V is L cube, so the gamma will be 3 times alpha. It's not alpha cube but 3 times alpha. So using this formula directly, this is a known established thing. So the volume that we want to find out for this, it will be L naught cube. L naught cube means 100, cube of 100, and then 1 plus gamma will be 3 times alpha. 3 times alpha value is 15 times 10 to the power minus 6, okay, and the temperature difference is 0 to 100 degrees centigrade, means 100 degrees centigrade. Now when we solve this thing, let me solve this, calculate this thing, it will be 15 times 3 means 45, okay, 1 plus 45, and 2 minus 6 means 10 to the power minus 4, and this will be 10 to the power 6, right, 6. So this will be what? When we'll calculate this, the value is, let me check, 45 divided by this plus 1.005 times 10 to the power 6 means I'm getting 1.0045 times 10 to the power 6 means 10045, and this will be the correct value of volume. Volume will be 10045. Yeah, this is the correct value of volume. So you can calculate like this way also. First calculate the new length and then calculate the volume, or you can directly use this way, this formula. Okay, now the next question is, Two metals A and B are of volume V and 0.99. Okay, so we have two metals. We have two metals A and B. Metal A has volume V. Metal B has volume 0.99 V. At 0 degree centigrade. At 0 degree centigrade, the volumes are at 0 degree centigrade. For A, volume is V. For B, volume is 0.99 V. And the coefficient of linear expansion. Okay, so alpha value for A material is 12 times 10 to the power minus 6 per degree, per degree centigrade. And for B material, alpha coefficient of linear expansion is 20 times 10 to the power minus 6 per degree centigrade. Okay, at what temperature will their volume become equal? Again, first this will be useful to here use this formula directly, that I want to use this formula, it will be better here. So expansion will be 1 plus gamma T. Again, since we are talking about volume, no, but I don't think, yeah, okay, right. So here the relation between alpha and gamma, I think we can keep. Two metals, what is the shape of this body? We have not been given, but okay, just why they have not given. They should give, because otherwise it would be difficult to calculate. I think these two metals, yeah, it should be, I think let's assume them to be cubic. Okay, then this gamma will be 3 times alpha. We have been given alpha already, so we need to find out that at what temperature these volumes will be equal. That means at what temperature VA will be equal to VB. Using this, V naught A 1 plus gamma of A, and the temperature difference is same, V naught B, okay, 1 plus gamma of B, and this V naught A. What is the volume at 0 degree centigrade? It is V. 1 plus, and this gamma is 3 times alpha A. 3 times alpha A. Alpha A is 12 times 10 to the power minus 6, and the temperature difference is, oh, we need to find out the T actually. Okay, V naught B is 0.99 V. 1 plus gamma B will be 3 times, right? 3 times 20 times 10 to the power minus 6, and T we need to find out. When we'll take these properly to one side, we'll see that this, let's make it, okay, if I would not have put the value, it will be a little, I think, convenient, but okay, when we'll try to solve this, we'll find out that T will be 0.01 divided by 3 times. When we try to solve this, okay, when we try to solve this, it will be 7. Volume, yeah, wait, volume we have, okay, actually V will get cancelled, and the remaining are numbers except T. So when we solve this, we will get something like this here. You can try and do, and from this we'll find out the value to be 427.35 degrees centigrade. So this is the correct answer. Okay. Next question is, the length of a metal rod is 80 centimeter at 20 degrees centigrade. So we have a metal rod at 20 degrees centigrade. Its length is 80 centimeter, and at 120 degrees centigrade its length becomes 80.16 centimeter. Calculate the coefficient of linear expansion. This is what we have to calculate, which we know. This is the formula, the change in length and change in temperature, 1 over L naught. So L naught was 1 over 80, 80 centimeter. The change in length is, if we subtract, we'll get 0.16. And the change in T, temperature, is 100 degrees centigrade. When we'll solve this, let me do 0.16 divided by 80 divided by 100, we'll get 0.00002. 1, 2, 3, 4, 5 means 2 times 10 to the power minus 5 per degree centigrade. Here, okay, to match our answer from here, we'll write it in like this, 10 to the power minus 6 per degree centigrade. Okay, so the correct answer here is this. Okay, so these were the questions for this session, where we did 3 experiments actually. Save this. So in this session we discussed about standing waves, we discussed about linear expansion experiment, and we also we also discussed the compound pendulum and coupled pendulum questions and did problems based on these things. So I hope you will be able to do the assignment questions now. They are mostly from this kind of similar problems, and the next experiment we will discuss in next interactive session. Okay, thank you. I'll stop the recording now.